Welcome geniuses, I'm Genie, your best buddy for A-levels. In this channel, we'll bring you to explore the secret formula behind success.
Okay, so the topic of quantum physics will be dealing with a new idea of looking at EM radiation. Because in your AS, right, you used to consider EM radiation as waves, right now. Okay, so scientists later on, that means after Newton's era, people like de Broglie and Einstein, so they actually found out that you cannot explain all the phenomena in this world if you treat EM radiation to be just as waves. So one of these phenomena that you cannot explain if you treat EM radiation as waves is photoelectric emission. So what is actually photoelectric emission, right? So this guy Hertz, right, what he did was, when he applied a voltage across two electrodes, right, he noticed that you need a very high voltage before sparks start to jump lah. So why will the sparks jump out at a very high voltage? Is because if let's say this is positive and negative, so then the electrons will be pulled to the left and the nucleus will be pulled to the right? So when the force is large enough, then the electrons will be stripped off the atom and then they will start moving, and so then you see the sparks lah. But what he also realized that if you use ultraviolet radiation, that means if you shine ultraviolet radiation onto these plates here, what will happen is the spark started to jump at a way lower voltage, which means to say the ultraviolet was actually causing electrons to escape from the surface. Alright, so the idea is, of course, we got to shine on the left hand side, so better draw for you. So you shine on the negative side, alright, so then you will get the electrons coming out from the negative plate and then moving on to the positive plate, so then you will see the sparks lah. So this phenomena, that means they found out later on that if you want electrons to be emitted from the surface of the metal, you will need EM radiation of sufficiently high frequency. So the phenomena of photoelectric emission, this is the definition: emission of electrons from the surface of metal when it's exposed to EM radiation of sufficiently high frequency. Now you will notice that different metals require different minimum frequencies. For example, like zinc requires ultraviolet frequency and above. That means if you use any frequency less than ultraviolet, no electrons are emitted, no matter how long, no matter how intense the blue light or the red light, not a single electron comes out. Similarly, sodium needs blue light frequency and above, cesium needs red light frequency and above. So this minimum frequency to cause photoelectric emission is called the threshold frequency, alright, which is given in your notes as well as your definition. So the first thing that scientists couldn't understand was this thing: why is there a threshold frequency? Because you see, if you consider EM radiation as waves, then there shouldn't be threshold frequency. Because the idea is, if let's say you had let me just change the color. If let's say you had this metal surface, and inside got a lot of electrons, if you shine ultraviolet onto the surface, then the idea is, then the electrons which are inside here will keep absorbing the energy from the ultraviolet. When it gets enough energy, it will escape, right? So if you use a lower frequency, let's say you use blue light or you use red light, the waves will contain less energy, but wouldn't that mean that you just have to wait a bit longer? Sooner or later you will surely be able to accumulate enough energy to escape, right? But it doesn't happen. See, so that is the problem. If wave theory means, if you consider that as waves, then there shouldn't be a minimum frequency. Whatever frequency that you send in, you just continue to absorb, finally it comes out when you get enough energy. But it doesn't happen like that. And the second thing that was puzzling scientists was the instantaneous emission of electrons. That means if you shine, let's say, ultraviolet and above on zinc, the moment you shine ultraviolet, it straight comes out. It is as if they don't even have to accumulate the energy. They just come out straight away. So the first two observations that show you that EM radiation don't behave as waves is number one, your instantaneous emission, number two, the existence of threshold frequency. So these two observations were puzzling scientists. So what they did next was to did another experiment. So the next experiment that they decided to do was to investigate what are the factors that affect photoelectric emission. So they actually considered two things. One is the intensity of the EM radiation. For example, if you're using blue light, a more intense means a brighter blue light lah. And the second thing they're testing is the frequency of EM radiation. So you don't use blue, then you use ultraviolet. You don't use ultraviolet, you use X-ray. So those are the frequencies of EM radiation. So they wanted to actually investigate what factor affects the number of electrons that are emitted. They call it the rate of emission. And number two, what affects the energy of the electrons when they are emitted. So the experiment is very straightforward. You have this tube here. C is actually your cathode because it's actually connected to your battery here, and D is your anode lah. So what will happen is, as you shine the ultraviolet onto zinc, for example, you will expect the electrons to be emitted, right? And they will travel over to the positive side because, of course, it's attracted to the positive terminal here lah. So the electrons which are emitted here will be attracted to the positives. So what will happen is, as the electrons travel, it will produce a current. Can you see that? So the voltage that you apply across the plates is measured using a voltmeter lah. So you plot a graph of current versus voltage. So logically speaking, the higher voltage you apply, the faster the electrons will move, right now, because it is more positive lah. Agree not? So therefore, the first part is logical, it rises. So let's look at the first curve first. So it rises here from 0 volts, and then it rises. So then many people ask me, why at 0 volts, you still have a current? It's because at 0 volts, if let's say this was just a wire, so there's no voltage here, if you shine the EM radiation, the ultraviolet on zinc, the electrons still escape, right now? So when it escapes, this plate becomes positive because it lost an electron. The electrons travel over to this side, becomes negative. So then the electron will travel back to here, from negative back to positive, or still got current. You understand? It's just that when you increase the voltage here, then it travels faster. That's why you get a larger current. Okay, but then they realize that when you increase the voltage, it will actually become constant. The current actually becomes constant. So your current cannot increase anymore. So why? It's because the current is defined as what? Rate of flow of charge, remember? Which is number of electrons times the charge of electrons over time, right? So what will happen is, the rate of emission of the electrons, let's say you're emitting 10 electrons per second. But initially, if you are using a low voltage here, what will happen is maybe only 5 or 6 electrons can reach per second. But when you increase the voltage, it moves faster. Now 8 or 9 electrons can reach per second, so your current increases. You increase the voltage more, then let's say 10 electrons reach per second. So that's your maximum current. Because if you try to increase the voltage further, you cannot have more than 10 electrons reaching this plate per second because you are only producing 10 electrons per second. So it is limited by the rate of emission of electrons. You cannot go higher than that. You understand? So that explains your maximum current. So if you get your maximum current, you can calculate the number of electrons emitted per second using back the same formula here. So if you know your maximum current, which is rate of flow of charge, which is number of electrons times charge of each electron. So your number of electrons per unit time is I over E. So you measure your maximum current, divide by the electron, the charge of electron, you get the rate of emission of electrons. Understand? So this is the first formula. So it's very, very useful, this first part. Then what they did was they increased the intensity. So they use a brighter ultraviolet, because ultraviolet is invisible, so you can't really see it. But let's say you use a brighter ultraviolet, just imagine. So they will get a higher current, which is logical. Because if you use a higher intensity ultraviolet, you expect more electrons to come out, agree or not? So therefore you get a higher current. Okay now, so this part is quite logical. You keep increasing the intensity, more electrons emitted, so therefore your maximum current is higher. So now we know what factor affects the rate of emission of electrons, which is intensity of EM radiation, which is logical. But if you wanted to investigate the energy of the electrons, then what should we do? We must reverse the polarity. So what do you mean by reverse the polarity? So remember your C and your D here. Instead of connecting it to negative and positive like this, we switch polarity. So now we switch this to positive and negative. But we still shine the ultraviolet onto the cathode, which is actually now not the cathode because it's connected to positive, but let's call it C. So let's call it C. So the electrons will be emitted from the C, but instead of being attracted to D, now it will be repelled by D, because now this is negative and this is positive, this is negative. So therefore the electrons here, which is trying to reach this plate, will now be repelled, right now. So instead of moving faster, it will start to move slower. So this negative voltage is indicated by this side, your negative voltage here. So as you increase the voltage here, more and more negative, it will start to slow down even more, right now. So therefore your current starts to drop. Can you see? So you keep increasing this voltage until there's no more current being detected here. Because remember your emitter is here. So the moment your emitter shows you 0 reading, it means that now there's totally no current flowing. That means what? You have stopped the most energetic electrons. You see, when the electrons are emitted from this surface, right, they will have, different KE one. Okay, why? Because some electrons are at the surface, so they need the least amount of work to escape from the attractive forces between the electrons and the nucleus. Because you see, when the electrons want to escape from the surface, they must overcome the attractive forces between the nucleus and the electron. Understand? So if they're deeper inside the metal, they have to do more work to escape. So they will come out with less KE. The electrons at the surface will be the easiest to escape. So you have comes out with the highest KE. So they come out with different KE, which explains why when you increase the voltage, not all of them will stop straight away. The current will decrease, because the more energetic electrons can still reach, but the less energetic electrons will be stopped. So you keep increasing the voltage here until the current becomes 0. You see this current 0? The voltage here is called the stopping potential. So what you have done is you have managed to stop the most energetic electrons. And we can calculate its energy now, its KE. Because the energy of the electrons is given in the topic of electric fields. When you try to stop it across, when it travels across a PD, the change in energy is QV, right now. So you have your maximum KE here, which is equals to QVS. That means this is the stopping potential. Because why? With this voltage, all the KE changes to 0. Because you cannot reach the plate anymore. So you cannot reach the plate anymore means the electron comes out and then it stops here. So all the KE here becomes 0 here. So the change in energy, which is KE max, actually KE max minus 0, is equals to QVS. Do you understand? So therefore, we get a second equation which tells us how to measure the maximum KE of the electrons. So first formula tells you how to calculate the number of electrons emitted per second. Second formula gives you the maximum KE of the electrons. But something very unique about this second observation, about this maximum KE, you notice that if I use a higher intensity, you would expect, since you are supplying more energy, the electrons should come up with more energy, right now. But do you realize, even with higher intensity, your stopping potential is the same? All three graphs have the same stopping potential. So what does that tell you? It tells you that the maximum KE of the electrons is independent of intensity of EM radiation, which is the third observation that puzzled scientists. Because if EM radiation are waves, and you supply more energy, so by right the electrons must come out with more energy, right? But it said no, you still comes out with the same maximum KE. Why? So later on, scientists found out there's only one factor that affects the maximum KE of the electrons, which is our next slide.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.